So, we're going to talk about exponential growth today.
Are we also going to talk about exponential decay?
And exponential decay.
Okay.
So, exponential growth. Usually, we're talking about populations. Okay. Do you remember, we talked about this already, do you remember what we assumed was true for population growth? There was an assumption we made. Had to do with like it being proportional. Yeah.
Something along the lines of it's not going to shoot down because of some disaster.
Yeah, so we're going to make those assumptions that there's infinite resources, there's no disease, there's no anything that's stopping it from growing. Okay. And what was the equation that we came up with for exponential growth? It was a differential equation.
P equals P naught?
No.
Times e to the RT.
That's what we came up with after the fact. But we had an initial assumption that we had in order to come up with that equation. You're right. It's good remembering. Remember? Let's talk about it in terms of rates. So, dp dt. Okay. So what do I mean probably? Because I'm talking about populations, I'm talking about time. So what does dp dt mean?
To change it, the instantaneous growth in the population at a certain time.
Can you say it without saying instantaneous, just like everyday language as much as you can?
The growth rate at a point in time.
Yes, the growth rate at a point in time. What do you think it depends on? The growth rate of the population.
The growth rate of the population depends on time.
Mm-hmm. What else?
It would actually depend on the size of the population.
Yeah, it would depend on the size of the population. Does it make sense? If you have a bigger population, you're going to have a bigger growth rate? Why?
Because there's more things to breed.
Yes, there's more things to breed. And so what we're going to make the assumption is, we're going to say it's equal to some constant k times the population. Okay. Where population is some function of time. But we don't know what the function that is. We're trying to find that. That's what makes this a differential equation. It's an equation based on rates and some unknown function of p, or some function of t. Okay? So how are we going to solve this? You came up with it before. You mentioned it before. What equation could I take the derivative of and get k times p? It's a function. What am I saying? P is so I have p equals some crazy function. I'm looking for that crazy function that if I take the derivative of it, it equals the same function but times a constant k.
The P naught equation.
A function that if I took the derivative of it, I get the same function, but it's times some constant k. Let's just forget about k for right now. Let's say k is 1. Okay?
If k is 1, it would be e to the x.
E to the x, or e to the t in our case, right? Because we're doing it as a function of t. Okay. So it's going to be something like that. So what if I wrote this? Oops. Get it out of the way. Let's do p equals a constant c times e to the I want to do it. Yep, that'll do. Now why? What if I took the derivative of this function?
You would get c times
What's the
it's a constant.
nothing that says what?
The constant. So in this one, they took the derivative of this. Let me do a screenshot here.
Can you make a little bigger, please?
We're saying some y. Okay. In this case, it's p that we're looking at. Okay. The derivative of y is equal to, and it's an equal sign here. Let's see. Equals. Okay. They're saying it's equal to this constant kt. But what they're doing is they're doing a k times a constant. K was a constant before, right?
Mm-hmm.
And this c was a constant as well. What's a constant times a constant?
A different constant.
A different constant. Okay. And they're saying that constant is just k. Okay. Whatever it is. C, you just pick c so that it ends up being k in the end. Okay. And that's what I'm saying right here. If I take the derivative of this, I'm going to get the same function times some constant k. Do you agree? What is dp dt here?
We have to do chain rule and product rule.
No product rule. Why not product rule?
Oh, because constant, the derivative of a constant, it's just zero.
Right. It's just a constant times a function, right? You're just going to be doing chain rule. So we're going to get the equation c times e to the kt. The derivative of this is just e to the kt times the derivative of the inside, which we get some k. What's a constant times a constant?
A different constant.
A different constant.
Oh, so you did a chain rule for the thing in, okay.
Okay. That's a constant times a constant. It's just another constant. Okay. So get used to this fact because we're going to start using that idea. Like, what's a constant plus a constant?
A constant.
A constant. What's a constant times a constant? Just another constant. A constant divided by a constant is just another constant. Sometimes we'll use a different letter to represent the fact that it's a different constant, but we could also use the same letter, understanding the fact that when you multiply constants, you just get constants out. Okay. It's a better form to actually just change this constant when I multiply this constant time. When I multiply c times k, I get some other constant. We call it b, for instance. Now, we want to try and find out what this constant is. So this is our equation. Okay. If I plugged in 0 for t, so p of 0, what would the equation become?
C.
C. So could you tell me what c is, based in the context of what p of 0 is?
It's the y-intercept.
What's that?
It's the y-intercept.
Yeah, but can you tell me in terms of what we're talking about, like with population?
C is the initial population at time 0.
Good. C is the initial population at time 0.
Oh.
Which is exactly what you said. It's the y-intercept, but you want to do it in the context of what the problem's talking about. So we get this nice little formula. P equals P naught times E kt. Now we just need to figure out what k is, but that's relative to whatever the problem is. So I'm going to save this guy. Let's try doing this. This is interesting.
Where did I get highlighted?
So use the fact that the world population was 2,560 million in 1950 and 3,040 million in 1960 to model the population of the world in the second half of the 20th century. Assume the growth rate is proportional to the population size. What does that little assume the growth rate is proportional to the population size mean?
It means assume that you can use this equation.
Assume you can use the equation, that's what they're saying. Okay. What is the relative growth rate? Okay, we need to define what relative growth rate is. Because you don't know what that is yet, I don't think. Do you know what relative growth rate is?
I
Okay.
looked ahead.
Okay, what is relative growth rate?
It's 1 over p times d p dt.
1 over p times dp dt. What does that mean in everyday language? I mean, it is relative growth rate in everyday language, but most people don't say relative growth rate. What am I saying by dp dt times 1 over p?
The inverse of the population times the instantaneous rate.
Yes. Now you're just using the calculus words. Try and define what it is.
The rate of growth in terms of the population size. So the rate of growth, it's the rate of growth times the inverse of the population, which means it's the rate of growth as compared to the population size. So you can compare the rate of growth with different population sizes.
Mm-hmm. So it's the rate of growth divided by the population size, or rate of growth per population size. Okay. What's that equal to according to our previous formula? That constant k. So what's the first question asking here? What is the relative growth rate? What are they asking you for?
Okay.
They're asking you to find k. Okay, let's do that. How do we find k? We know that population is equal to initial population e to the kt. So what are we looking for? K.
You can just plug in the two population sizes they give you,
Okay.
and then the difference in time.
Okay. So what's our initial population going to be?
2,560.
Yes. 60 times e to the k times, well, let's figure out what the final population is going to be.
It'll be times e to the 10k.
We'll get to, we'll get that 10 in here. 10 years. So what's our population after 10 years?
34.
Now it should just be algebra solving for this, so we can figure out what k is. 3,460 equals e to the k times 10, or 10k. Okay, now what?
I solved for the fraction.
Hmm?
I solved for the fraction. So do you want me to do the rate?
Oh, sure. The decimal? Go ahead.
P over P naught.
Then you take the natural log of both sides.
1.1875.
1.1875 is e to the 10k. And then what did you say?
You take the natural log of both sides.
Take the natural log of both sides. So natural log of 1.1875 equals what?
10k.
10k. And then we just divide the answer by 10 and we get what k is.
Point 0171850257257.
So what was that k again?
0.017.
.017. Give me a few more.
185.
Okay, so that's okay. Use the model to estimate the world's population in 1993 and to predict the population in the year 2020. I'm going to change the problem here. Do you guys remember what's that?
You can do that?
I can. I'm just going to change it.
Only he can do that though.
Oh.
Let's see how good of a model we have. Okay. Do you remember a big event in terms of population last year? Do you know how many people are on Earth?
7 billion?
Yeah, over 7 billion now.
More.
Mm.
Do you know what happened last year?
We reached 7 billion?
We reached 7 billion in 2011. We reached 7 billion on apparently October 31st is when we reached it.
That's interesting.
Okay. So if this equation is any good, okay, and these two data points are any good as well, then we should be able to predict when we should have hit 7 billion people. Do you think it's going to be exactly on October 31st in 2011?
No, it's gonna tell you the year.
Yeah, it's going to tell you the year, but we're going to get a decimal. We could also extrapolate that to months, right?
Mhm.
And days and hours and seconds and stuff, if we wanted to. But we'll see if we get. Are we going to get an exact year? Is it going to match? What do you think?
Probably not.
Why?
Because this model
It's
isn't
just not
perfect.
enough information. Like, if they gave you 3 data points instead of 2, you could come up with a more accurate one. And if they gave you 4, you could come up with a more accurate one. It just seems like if they give you a population.
In 1950 and 1960.
Yeah.
So it seems like we'll get really far off or something.
Yeah, absolutely.
And what did you say?
It's just not a perfect model because population isn't unrestricted growth.
Correct. Population isn't unrestricted growth. We have wars. We've had wars since 1960. Yeah, population gets affected by that. There's disease. There's a lot of other factors in here, but let's see how good it is. Select this.
So cool that you do that.
Page.
You know?
Yeah.
I need to resist the temptation to say silly things just so it goes up on YouTube.
Well, I appreciate that. Okay. So we've got this. Let's see when the world population is going to hit 7 billion. So how am I going to use this formula to do that?
We start with the p equals p naught e to the kt.
Equals P naught E to KT. Okay.
And then for p you put 7 billion.
Do I put 7 billion or do I put something else? I put something else. What do I put?
You put however many millions 7 billion is.
Yeah. So this was 2.5 billion. This number right here was 3.04 billion.
So you put 7,000.
7,000. Equals initial population.
You
Let's
could
put our-
use either of those two.
I could use either of those two. I'm going to use the first one. Okay. 2560 e to the power of constant 7185 times t. And now I just take the ratio of it, divide by this constant up here after I take the logarithm, so I get t, I do the algebra, is the natural log of 7,000 natural log of 2560 all divided by 4.7185. Go ahead and do that in the calculator, see what we get. By the way, I did the difference between logarithms because it's a ratio. It's the natural log of 7,000 over 2,560, and it's the ratio of two things inside a logarithm, and write it as subtraction on the outside.
I got 58.5337.
58.5337. by 3. So if we're using years, let's just call that 59 years.
Yeah.
Okay, how good did we do? We know when we did 7 billion. It was last year, 2011.
We got 2009.
2009. How does that strike you as an answer?
It's a little bit low.
A little bit low.
It actually sounds reasonable, because what would happen would be, what it's actually saying is that it's giving us a lower number, and it's saying that because of all these things that happened in those times, we had 2 years to compensate for the decrease in world population. So if we were supposed to reach that in 2009 and we actually reached it in 2011, those 2 years from 2009 to 2011 make up for the decrease in world population between 1950 and 2009. That's what it's actually saying.
I would just say that it was a little bit. What happened to K? In reality,
It fluctuates.
it fluctuates. Why does it fluctuate? Because we have all these things happening. This was just based on the 10 years between 1950 and 1960, and it was able to predict between 59 and 61 years into the future of what the world population is going to be, and it's fairly accurate. That's over half a century in the future is able to predict. It's a pretty impressive fact. Does that make sense? It's a robust formula. If you can predict 61 years in the future with that formula, so it's not far off. Does that make sense? It's only off by 2 years. It's pretty good. Okay. So what must have happened to the formula, or what must have happened to K? Did it increase, decrease?
In real life, K must have increased.
K must have increased because K must have decreased in order to project it out further. So here's a formula. A bigger K would predict a bigger number in the same amount of time, right?
Oh, right. Okay, so K must have decreased.
K must have decreased. Just by a little bit. Not by much, though. In fact, it could have been because we didn't go out far enough with our K here. Does that make sense? But it's pretty good. So if I asked you to predict what the world population in 2020 was going to be, do you think this formula is going to work out pretty good?
Pretty well.
Yeah.
Pretty well. It'll probably predict fairly closely how much the population would be. So let's do that. What's the world's population in 2020? P equals, let's use the same one, 2560 e to the k t. We're going to plug in for t.
2020 minus
1993,
1950.
So that would be 70?
Yeah.
T is equal to 70.
Oh, are we doing 2020 or are we doing 1993?
2020.
Oh, then that's just 70.
So what was the world's population?
Oh, yeah, to do that now.
Yeah.
$233.09 million.
233.
No.
No. I can write numbers. I can do it. 233.
Which doesn't look right.
No, that doesn't look right at all. Saying our population decreased.
I
in
got
2020.
30,
Oh, I see what I did wrong.
I got 3039.
39. You're saying your population decreased again.
Yeah, I must have done it wrong. Yeah.
8,524.6 million.
8,000. Say again.
8524.6.
8524. Can you do 0.6. million people, so that's 8.5 billion people.
Mhm.
More
Yeah,
realistic.
I just got that. I put in the wrong time.
How far off do you think it's going to be before we get to 8.5? Maybe a few years. Could be a lot more though, because when you start projecting even further down the line, there's a lot of gray area on what that K is going to do.
Statistics.
Yeah, more data, but it's a pretty robust formula if we predicted that it's going to be 7 million people in 2009. Okay. Any questions? What other formulas do you think, or what other things could we use this basic formula for? We're talking about growth rates of things. It doesn't just have to be population. It could be something else. What else?
We have
Stop looking ahead.
I'm not. I'm looking ahead, but I wasn't looking. I wasn't reading while I was talking.
Okay.
If we have either a negative, and we can have a negative. No, we could have a negative.
If K was negative, it would be
a
exponential
negative
decay.
K or a decimal K, the population would go down.
We had a decimal K.
No, a negative K then.
Negative K. Yes. A negative K would be saying the population is decreasing. Okay. But what other types of things? It doesn't have to be population. I know you can say like bacteria would be an example, but it's still the same thing as people growth. It doesn't really matter. So what other things have this sort of growth rate that depends on the size of the population?
Fibonacci numbers.
They grow in a different way, an interesting way, a different.
Okay.
Not
But
necessarily.
if you think about the rabbits, that's a population growth.
What if I said something?
You're right. You're 100% right. It's going to go in the same way, and it's going to be in the form 2 to the k, which 2 to the t, which you can transform into this equation if you wanted, which would be e to the power of something, because it would be. What would you do? If you have 2 to the power of t, you could change that into e to the power of natural log of 2. Yeah, so then k would be natural log of 2 in that case. But what other things have growth in? Yeah.
What if, could you do it with decimals? Like if I wanted to say a density of a certain chemical in the air, and it's the density is this amount of this year, and it's this amount at this year. Can you find the rate of
You
change?
kind of looked ahead and now you're half.
No, I didn't. I really didn't.
Hodgepodging it together. So the other thing that we could have is, for instance, money. How would money be like with this growth sort of thing? Money in a bank account.
Well, if it's being. Oh, I see what you did there.
Yeah, what did I do?
You were like, if you're compounding continuously,
Uh-huh.
then it has to do with like this equation.
It exactly has to do with this equation, because the rate at which your money grows depends on how much money you have in. Does that make sense?
Mm-hmm.
So if you have more money in, you're going to have a bigger growth rate. It's exactly the same formula if you want to do compounding. Same exact thing. What about?
No, you're not gonna have a bigger growth rate. You're gonna have a bigger revenue. That doesn't mean a bigger.
Your growth rate, the growth of your money, is definitely like how fast your money grows over time. Definitely depends on how much money you put in.
Right, but if I put money into the bank, say $2,000, and they said we'll give you a 3%
Interest rate.
interest rate, which is huge in this economy.
If it's just a savings account, yeah.
But if what's going to happen is that 3% is going to be flat if I leave it, say, 40 years. If I leave it 10 years, it's going to be 3%. If I leave it 40 years, it's going to be 3%. But the amount that 3% is spitting out is going to be different. So the actual rate doesn't change.
The rate does change. The rate that your money grows changes over time. Because you're going to get, let's just do simple interest. So if you do 3% on $100 that you put into the bank, okay?
Mhm.
How much money do you get in the first year?
103.
You have $103.
Mhm.
Then the next year, how much do you get?
More.
More than $3, right?
Yes.
Why?
Because I have more money to begin with.
Correct. So your growth rate the rate that your money grew was bigger in that second year. Does that make sense? Because you had more money in there. So if you started out with more money, as opposed to $100 to say $1 million, then you would get that, whatever 3% of $1 million is. What's that, 300? I want to move the decimal place over in my head. What's 3% of $1 million? Chop off 2 zeros.
$30,000.
$30,000 at the end of the year. That's not so much out of $1 million.
And a 3% interest rate.
And a 3% interest rate. You're going to get $30,000, but then the second year you're going to get more money than that, right? You're going to get You're going to get that $30,000 again, but 3% on top of the $30,000 as well. So it just keeps getting bigger and bigger. The growth rate totally depends on how much money you have in your initiative. So that's another example, money. Another example is half-lives.
Ooh. Half-lives.
Now, half-lives isn't growth. What's half-lives?
Decay.
It's decay. Okay. Let's see. There we go. It depends on the mass that you start out with, but in exactly the same way. So, you take this guy. Change in mass over change in time is equal to k times the mass. The more stuff you have, okay, the more it's going to decay. More stuff, it's going to decay. Does that make sense? And it's going to have that same thing. But in this case, we're going to get a k that's a negative number. Okay, that's the only difference between the growth and the decay. A positive versus a negative number. Okay. Let's go back to the calculus textbook. Formula ends up being, as I hope you would expect,
If I had
how does that compare to the population equation?
growth rate of 0.
It's identical.
It's identical, except they changed p for n. Okay, the mass of something.
If I had a growth rate of 0, that would just be like you're not making anything, right?
Yeah, the population would stay the same. In that case, you'd say k is 0.
And E is 0 is 1.
Is there any example that would actually happen in real life?
Sure, put your money under your mattress.
Although its actual value is decreasing because of inflation.
True, but we're not talking about value, we're talking about how much money's there. We got inflation and stuff like that. Same with mass of materials. If K was, like, if there was no half-life, which everything has some sort of half-life that decays at some point. It's just that some things are longer half-lives than others. K would be 0. So if K is positive, we've got growth. If K is negative, we get this decay. Does that make sense? So it's the same exact formula. Try a problem. So I shouldn't be able to stump you with this because you should feel like it's the same problem. Oh no. How do I do this?
Just use the computer.
Try not to. That's good. Practicing. So the half-life of radium-226, so in case you don't know chemistry, what's the 226 referring to?
Mass.
Atomic mass.
Yeah, the atomic mass. Is 1,590 years. What does that mean, the half-life is 1,590 years?
That's the amount of time it takes for half of it to decay.
Correct. Does that tell you what K is?
No, indirectly.
Indirectly it does, but it doesn't tell you what K is. So a sample of radium-226 has a mass of 100 milligrams. Find the formula for mass of the sample after T, that remains after 2 years. So A should be fairly easy. What's my formula? Well, I need to find K. How do I find K?
So you know that the formula is m equals m naught times e to the kt. So you can plug in the initial mass and half the initial mass for m naught and m.
So I could do this. 1 equals 2.
That would be easier.
Magic. 1 equals 2.
1 kt.
Mm-hmm.
What's t in this case?
1,590 years.
So it's 1/2. And if I do the natural log, so of both sides, I get. Let's see if I can do this simplification and get why it is. When I have negative element too. I did the natural log of both sides. I skipped a couple steps.
Because the natural log of 1 is 0.
0. And the natural log of 2 is the natural log of 2. And the natural log of 1 over 2 is the same thing as the natural log of 1 minus the natural log of 2. That makes sense, or should I write it down?
No, it's fine.
And so what's K?
It's got over 59.
It's, which is
Negative
negative
4.35 times 10 to the negative 4th.
negative 4th.
Yep.
Round it down.
Yeah, I rounded down. I should have rounded up. Make it 4.36.
3/6.
Or just 359, whatever.
Yeah.
That's K. So how am I going to find formula after K? Here's just plug in K to that original formula. You're good. That's easy. Find the mass after 1,000 years to correct to the nearest milligram. How am I going to use it? It's just the formula. Do I need to go over that, or are you guys okay with this?
No.
Rachel?
I'm good.
When will the mass reduce to 30 milligrams? That shouldn't be that hard either. I don't do that.
You just plug in 30 for m and 100 for m naught.
Mm-hmm.
And you have k and you find t.
Solve for t. Do the natural log. Okay. Let's get that. Good. How much time do I have? No time.
10 minutes.
10 minutes?
12
It's
really.
much faster teaching you this. When I only have 2 people in the classroom. Okay, Newton's law of cooling. This is also the same exact thing as population growth, except we're talking about decay in this case, as the temperature goes down. Okay. But what's going down, we're talking about temperature. So what Newton said was the rate at which the temperature changes. Notice they're using dt. Very hard to say. Understand what you mean.
Well done. Isn't that just 1? I love the fact that
Here's
if I
Newton's
don't
law
have
of
to, you
cooling.
guys get it.
Yeah, so dt in this case. What's the first dt? Top one.
The change, the instantaneous change in temperature.
Yes, over the instantaneous change in time. He's saying that the bigger differential between the temperatures of an object, like say, if something's at boiling, okay, let's say 212 degrees Fahrenheit. Okay. He uses Celsius, so 100 Celsius. Something's at 100 Celsius and it's put into a freezer. So let's say the freezer, even though this isn't correct, freezers are usually below 32 degrees Fahrenheit, so 0. Okay, so you take something that's 100 degrees Celsius and you put it in something that's 0 degrees Celsius. He's saying the rate at which the temperature changes is the difference between those two, times a constant. Okay. Would that make sense? The hotter something, like, what is he effectively saying? He's saying that the temperature, the heat, will move out of it faster the hotter it is.
Yeah.
Yes.
Yeah. Okay. Now, what is this formula that we got a T minus Ts, so that's the surrounding temperature.
Oh, okay.
That's the surrounding temperature, so that's a constant. You see that? And T is the temperature
Of the thing.
of the thing. We don't know what the formula is for it, but it's not too hard to figure out. Let's just temporarily call this this function, let's call T minus T sub s, let's just call it y. Okay? Now what does the formula look like? K times y.
Oh, okay. I see what you did.
The change in temperature, I should really change this capital T into some sort of y, but you kind of get the idea here. The formula would end up looking like if this was, instead of having dt dt and dy dt, now I'm doing a little bit hand wavy, but we can fix it. This is kind of what it's supposed to be. The formula would look exactly the same as the other ones. It would be y equals y initial e to the k t. Is k going to be positive in these examples or negative?
Negative.
Why?
Because if you have a cooler, because the temperature is decreasing.
Because the temperature is decreasing. Okay. We've got this decay sort of action.
No question.
But this formula is a lie.
I could see why it would be.
I can
What's
see
that?
I could see why it would be a lie.
Yeah.
Because he's saying for cooling, not for heating.
Well, no, because you said that T minus T sub s is y, but that's not equal to T, so you can't replace the T with the y, so that's why.
We have an initial temperature. E to k t. So formula becomes this. It should look very similar because it's the same idea. Capital T 0. E to the kt plus starting at temperature. Okay. It should look pretty similar to the other thing. You just say add on the temperature that you start at.
I have a question. What if you have a cool thing in a warm environment?
What's that?
What if you have a cold thing in a warm environment?
Cold thing in a warm environment, then you'd have an increase, and then k would be positive, but it would be the same formula.
But it wouldn't be an exponential increase. It would be more like a negative.
Oh, yeah. But k would be positive. Yeah, we'd have to change the formula.
I think T would be negative, maybe.
Which t?
One of them.
I mean time or temperature?
Time.
Time would be negative.
I mean temperature.
Temperature would be negative?
Yeah.
Yeah, we'd be talking about negative times. I'm going to have to think about that one. I don't have a quick answer for you.
Okay.
Let's just check to see if this is right. Now, we know in this example that k is going to be a negative number. Okay. What happens as t goes to infinity, as time goes on forever? What does the formula become?
Negative. Depends on k actually. If k is positive or negative.
If k is positive, yeah. If k is negative, that becomes e to a very large negative number. So T approaches the surrounding temperature.
The formula becomes this. Because this section, right here, it becomes e to a negative infinity, right?
Mm-hmm.
What's e to the negative infinity? Really close to 0. Right? 0 times this thing is going to get you 0. And then you're just left with this. Does it make sense? As time goes on forever, should the temperature equal the surrounding temperature?
Yes.
Yeah. So we've got somewhat of a valid equation here.
Hand wavy, but valid.
It's not hand wavy. I just don't have the math to really show you how it works. We'll get to differential equations. We're just introducing the idea of differential equations, but we don't have to make it hand wavy. Right now, I do. Okay. It's okay.
So you just waved your hand, it's hand wavy.
I know, but I can't see that on YouTube. Okay, so this shouldn't be any difficult to use this formula in order to solve problems. It's really just algebra at this point. I just wanted to get you the idea of what a differential equation is. Okay, because we're going to be creating them in our next section. Okay.
Sounds lovely.
I think we're done. So let me assign the homework.
Can I have some, can we have an example for example 3? I don't really understand it. The one that's talking about the bottle of soda pop. Weird.
Soda pop is at room temperature, 72, is placed in a refrigerator, it's 44. After about a half hour, the soda pop is cooled to 61. It's cooled to 61. What's the temperature after another half hour? And how long does it take for the soda pop to cool down to 50? Okay, so they're using the same exact formula, except they're just doing it. I mean, yeah, we can do it. It's not bad. We'll use my formula. Actually, no. What's this?
Original time. The original temperature.
Original temperature. So in our case, it's going to be what?
The original temperature.
What's the original temperature?
72 degrees Fahrenheit.
72 degrees Fahrenheit. What's T sub S?
44 degrees Fahrenheit.
44 degrees Fahrenheit. K we have to find. But they told us after a half hour, so what will we plug in for T? Time.
0.5.
Sure. Or you can plug in 30.
Either way.
It depends on what you're talking about. Since we're talking about in minutes, I'd probably plug in 30 minutes. And they told us what the temperature's going to be, right? After 30 minutes.
Mm-hmm.
What's the temperature?
61 degrees Fahrenheit.
So right here, you're going to plug in 60.
Okay.
And
61.
And then you solve for K,
Wait, and then TS is,
the surrounding temperature,
which is 44.
44.
Okay.
And you solve for K.
Okay. That's not bad.
No, it's not. The reason why it's confusing is because they didn't remember my hand wavy stuff. Okay. They just didn't come up with a nice little formula for it. But it's the same stuff. So if I was going to do part B, once I know K, what's the temperature of the soda pop after another half hour? So I plug in 60 for time.
Mm-hmm.
And I already know my K because I figured that out in part A.
That rhyme.
I know my K, I plug in 60. I know my surrounding temperature, I know my initial temperature, and then I can figure out what the final temperature is going to be.
And if you put in 0.5 for half an hour, you could just say T equals 1.
Yeah.
Instead of a lot nicer.
Either way, it doesn't matter. If you want to do it in terms of hours or if you want to do it in terms of minutes, it's okay. We'll just find a different K for both situations. Does that make sense?
Mm-hmm.
But you'll still get the same answer. Okay. Now the homework. Let me stop recording.
Phil's gonna torture us now. If this is going up on YouTube. People of the internet, please help us.
I thought you said you were restraining the urge to say stupid stuff.